once they join the CITA, they can apply to the CITA National Fellowship.
Shall I start? I don't need an introduction because I put it up there.
Well, I should introduce you anyway, just for the sake of decorum. Hi, everybody. Thanks for coming up to CITA. This week we have Douglas Scott, who's a professor at University of British Columbia, and he's going to be telling us about some neutrino physics. And as you can see here, he has many long story connections with CITA. So we're pleased to have him back.
I was just trying to remember my connections to CITA, so I thought I would write them down. I got to that age where I don't remember anything unless I write it down. But I have been here a bunch of times before. And I think I've had at least 4 CITA National Fellows, but I lost count. And a whole bunch of students that worked with me have been through here. So I mean, I have many connections, but I haven't been here for like a decade. So I was in Waterloo last week and I thought, hey, I'll go to CITA for a change. I came here when I was a grad student.
That was 10 years ago?
Sorry?
That was 10 years ago?
19th century. Encouraged by my father-in-law, who was also an astronomer. I think he was one of the, I mean, I know Peter and Dick, other Dick, were the founders of CITA, but there was like some proposal that people signed saying something like CITA would be a good idea. I think my father-in-law was one of the signatories of that. Paul Feldman. Submillimeter, he was a theorist of pulsars and stuff, but then he became a submillimeter designer. Anyway, so that's that. And I looking for the CITA logo, I noticed that lots of people have been copying CITA, and it's like all over the place. And there's all sorts of weird and wonderful things called CITA. I thought I would also say that when I was here, maybe the second time, I stayed in Massey College, which is lovely. And we arranged for me to stay there, but I couldn't stay there for the whole time. So although one thing I remember about Massey College is the first time I was there, the corridor I was on reeked of cigar smoke, like, and you're not supposed to smoke. And I went to breakfast and said, "What the hell's with the?" And they went, "Oh, Mordecai Rickler." And I wasn't very Canadian then, so hadn't heard of Mordecai Rickler, but he's a very famous Canadian author. So I never met Mordecai Rickler. He died a couple of years later. So I never met him, but I did smell his cigar smoke. And that's what I remember about. But this time in Massey College, there really wasn't no smoking policy. Presumably he got away with it because he was the visiting author or whatever. So for the other nights, I looked around. Toronto's almost as expensive as Vancouver in the summer. Not quite, but it's close. So I found an Airbnb place that's just a block from this corner. I don't know if you can read the signs, but this is from Street View, and it actually looks much worse than it did when the Street View thing. But so this is supposed to be the most dangerous intersection in the whole of Toronto. And there were a whole bunch of people hanging about. They all seemed pretty friendly and harmless to me, but I'm a tall guy, so it is a strange place to end up living. But I'm seeing at least 2 different sides of Toronto. Okay, but what I want to talk about today is the cosmic neutrino background. So it's sort of really just a bunch of bits and pieces of nonsense. So nothing that I'm going to tell you about matters in anything that you're doing. But hopefully it's interesting and hopefully mildly amusing, and hopefully you learn a couple of things that you didn't know before. And I spent ages figuring out how to do this transition, so I'm going to show you again. This is it's a metaphor for neutrinos. There's 3 colors. We're all aware of the cosmic microwave background. I've worked on this a lot. This is this is a picture of the universe taken from outside the universe, right? So that you can see the CMB sky. My approach to understanding the neutrino background comes from being a CM-bologist, as we're sometimes called. So that's really the philosophy that I'm going to adopt. But let me, in case everybody falls asleep, let me give you the summary first. So this is everything that I'm going to say. So let me read this. I mean, I know you can read, but let me read it for you. Neutrinos are very hard to detect. They come in three flavors. They mix. We don't know why they mix as much as they do compared to the quarks that don't mix very much. We don't know whether they're their own antiparticles or the Dirac or Majorana. We don't know how the masses are ordered. Is it the so-called normal hierarchy, where there's sort of three things, or is it the inverted hierarchy, where one of the mass differences is two things that are very close in mass? Cosmological neutrinos, if you thought regular neutrinos were hard to detect, are really hard to detect. There's about 340 for every cubic centimeter, so just right here, there's 340 neutrinos. There's 411 CMB photons per cubic centimeter, so they're the second most common particle in the universe, unless you count gravitons. That's complicated. If we could detect them, they'd be interesting, but we can't. But I'm going to tell you what you could do if we could detect them. Right? If you want to know more about neutrinos for real, in cosmology, I highly recommend this review article by Julien Legourg and Misha Verde. This is the 2024 version. It's in the particle data book. If you don't know what the particle data book is, you should and read it and so on. I'm an author, so I get another citation if you read it. This is being currently updated. There's no major updates about neutrinos, except we've had a big email exchange about what to do with negative neutrino mass. But I don't think they're going to make a big fuss about that. It's just going to be mentioned. Neutrinos almost certainly don't have negative mass. Just a summary of what neutrinos are. So they're very hard to detect. The sun produces a lot of neutrinos. It completely dominates if you counted all neutrinos. So there's a lot more in this cubic centimeter from the sun than from the background. They're produced prodigiously in the sun. Every nuclear reaction makes some neutrinos. So you can work out at the Earth, there's about 10 to the 15 per second entering your body, right? And the number leaving your body is 10 to the 15 per second. I tried to figure out what's the chances of a neutrino interacting with your body in your lifetime, and there's like physics stack exchange discussions up the wazoo, and the answer is of order unity, but with a dispersion among gases of 10 orders of magnitude or something. They're all over the place. It depends exactly what you mean and what energy neutrino is and blah, 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 blah. But if you're worried about that, right, then you should just make sure that you always point your head towards the sun to minimize the cross-section. Then it'll be slightly less than 1 for your life. Right?
That's not how we stand up vertically.
There's this well-known poem that people often get. I'm not going to read it out to you, but it's John Updike, who's a very famous poet, wrote this in the 60s, I think. And it sort of goes along with this fact that when we first detected extrasolar neutrinos from supernova 1987A, right, first detected by a Canadian, you know that. Something like, there were experiments detecting neutrinos. There was a sort of excess, and it's Poisson statistics and so on, but of order 20 extra neutrinos. Almost all of them were detected at night. So the neutrinos were going all the way through the Earth and up through the bottom of the detector, right? Just to illustrate to you how hard to detect they are, and it sort of connects with the poem. So what about neutrinos in cosmology? So it's usually called either the CNB or the C nu B. But that sounds a bit like C nu B. Plus, it's really hard in tech to get a nu to look like a nu and not a V. So I do CND, right? Let's start with a coincidence. Because we know the number density of neutrinos, the total density, mass density, and energy density of neutrinos is just proportional to the neutrino mass. So it turns out when you do the sums, it's the sum of neutrino masses divided by this number in electron volts is omega in neutrinos. Right? For the normal hierarchy, omega nu is 0.014, 0.0014. Okay, and that should be compared to, it's 5% in baryons and 20-something% in cold dark matter. Right? So it's a small fraction, but not completely negligible. Just to contrast with that, the average density of stars in the universe, and this varies by factors of several, depending on who guesses it, but I took Fukugita and Peebles because they're smart, famous people, and it's the best one to grab from the literature. It's 0.0015. These numbers are the same, right? So there's the same total density in stars in the universe as there is in neutrinos. So if you want to write a paper explaining why that is, because it's not a coincidence but a piece of physics, you're welcome to do so. You just have to acknowledge me. And I don't need to be a co-author, because it would be crazy. So these are essentially the same. So what does that mean? I mean, other than this crazy coincidence, it tells you that neutrinos are some of the dark matter. Right? So they really are part of the dark matter. They're not completely negligible. They're small enough that you can almost ignore them, but not quite. And another way of saying the same thing is that if the mass was much bigger, they would be the perfect dark matter candidate. So I have hardcore astronomy colleagues who are not sure that dark matter is real, because they only, when they see a star or they sit on a chair, it's like a real thing. And this dark matter thing is nonsense. I assume they believe in neutrinos. I mean, I don't know. I haven't asked every single one of them. If you believe in neutrinos, it's a small step to believe there's something else like neutrinos that's heavier. So I do not understand why people want to reorganize gravity so that it doesn't conserve momentum and blah, 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 blah. When all you need is some slightly non-shiny stuff, like neutrinos. So that's what that tells you, right? So they are some of the dark matter.
Yeah, but they're kind of hot.
They're hot. Yeah. They're
Perfectly good dark matter.
I've never seen one, right? But I've read stuff where people have seen them, and I don't disbelieve that they exist, right? And all you need is one other thing that's harder to detect. So let's talk about photon backgrounds in a way of building up to neutrino background stuff. This is the first plot that I'm aware of that plotted the background radiation at all frequencies or wavelengths. Right? This is by Longair and Sunyev. Malcolm Longair had some kind of visiting thing in Russia, so he went to Moscow for 6 months or a year or something. He'd spent a bunch of time hanging out with Rashid Sunyev. They wrote a couple of conference proceedings, and for about 15 years, they referred to the book that they were writing together, in which this would be described in great detail and so on, and the book never appeared. So it was one of these famous long-term, somebody was telling me something about Bond and Myers patch paper 3 that never appears. It's a similar thing, paper 4. 3 did appear.
3 exists.
But 4 never exists.
4
So
doesn't
Longair and
exist.
Sunyev was the same thing. So Dick was just they had almost no data when they made this plot. But these are smart people, and this is almost completely correct, despite having almost no data, and almost completely correct at all wavelengths. There was a compilation put together by a guy called Ted Ressel, who was a student of Michael Turner. Michael Turner wanted to know about constraints on decaying particles that turned into photons. So he wanted to know what the backgrounds were at every wavelength so you could constrain different energy dark matter candidates that turned into photons. So he got Ted Ressel to combine all the existing data And they produced a paper in an obscure journal that used to be hard to find, but now it's on PBS. And they called it the Grand Unified Photon Spectrum. Okay, Ted Russell then moved into nuclear physics, so this was his last dabbling in kind of astrophysics. But when he moved into, I met him a whole bunch of times. When he moved into nuclear physics, I was working on trying to do something similar, so he gave me his SuperMongo scripts. Hands up if you know what SuperMongo is.
That's depressing.
Old people in the room. So I put together this thing about a decade later, where there's upper limits and lower limits for various reasons and measurements and stuff. And various other people have done this, particularly in the optical and the IR, where there's a debate about which one's bigger and so on. This is a review article by Dole et al., but they have wavelength along the x-axis, so I had to flip the curve so that it's right in the same.
At least you both went to New Elm instead of Elm.
Yeah. Why is this interesting? So it tells you about the integrated history of electromagnetic radiation through the whole universe. So in particular, the CIB, for example, tells you about star formation history plus AGN, which contribute and stuff. So you're learning about black hole accretion, plus the history of star formation in the universe. And potentially you're learning about crazy things like some particle that decays or other kinds of exotic physics. The absolute level is really hard to measure, so it's easy to add up objects, and I've spent a lot of my career doing that at different wavelengths and trying to get it right. How many years ago now? 7 years ago, or it would be 8 years ago, I had an undergrad called Riley Hill, and I gave him the task as an undergrad to do a new compilation and use this thing called Python rather than SuperMongo. Right, which he was quite good at. He had never heard of SuperMongo, but he converted the scripts and made this very nice compilation. And then Riley became my grad student. We collaborated with Kyo, who was a grad student here? Yeah, grad student here. Who contributed a whole bunch of things. I want to show you now a picture of Bob Kirshner. Why am I showing you a picture of Bob Kirshner? The joke that I've heard him tell the most in talks, he's very funny. I mean, it's not as funny as me, obviously, but he's quite funny. Is the following, right? So because he did a lot of spectroscopy in his career. So he likes to say that a spectroscopist to some view takes a rainbow and turns it into a graph. So we decided to take a graph and turn it into a rainbow to be different. So I said to Riley when he was an undergrad, I kept giving him tasks and not telling him how hard it would be, and he just did it anyway, because it's right? Can't tell them that it's challenging, because it breaks them. So I said, I sort of imagine a rainbow, because rainbows are cool. And I imagine that everywhere where the data are uncertain, you put a big sort of splatter of points. And where it's not, you put an arrow. So I call this a splatter diagram. There's probably a name for it in some other field, but it's a splatter diagram. And Riley made the splatter diagram that was way better than the thing I had in mind. And I obviously said, that's exactly what I had in mind. Well done. Seems like a day for telling side jokes. So I'm reminded, I ran into Bob Kirshner recently, and I asked him to confirm that this story I'd heard about it was true. Because I told this joke several times about, and he confirmed that it was basically true. So the joke was, Bob is incapable of not saying one-liners. People called him the David Letterman of astronomy for a long time. So he just blurts out. So apparently 20 or 30 years ago, I think it was before like 9/11, but still serious airport security. He's in an airport, he gets on a plane, sits down, a lady comes to sit down and says, oh, you're in my seat. And he says, oh, don't worry, they'll be able to tell us apart from the dental records.
Oh my God.
And he's overheard by the cabin crew hauled off the plane, and given the third degree for, and he swears that this is actually a true story. I have to say, no, you misheard me. What I said was, I forget what, he made something up. Anyway, sorry to, I might get to the end of the talk in an hour, but I might not. Okay, so well measured, not very well measured. And what this is telling you about is, well, all of this stuff is gravitational physics, because it's AGN. Right? The stuff in the middle is nuclear physics, because it's stars. So it's either direct stars or reprocessed starlight. The CMB is the early universe, right? And then the radio is complicated. But you're learning about all these physical processes in the history of the universe. I'm assuming that you have heard of the CMB, and in particular, because this is Canada, and we know that the microwave background was discovered in Canada in 1940 by McKellar, right? So this is a picture of the unveiling of the Dominion Astrophysical Observatory 72-inch telescope, which was the biggest thing in the world for 5 minutes, I think, but it was the biggest thing in the world. They did spectroscopy like you couldn't believe. I think, I mean, maybe during the war it was easier to get telescope time or something, but McKellar had it as his private telescope almost for a while, and just did lots of stellar spectroscopy, and included in the stellar spectroscopy were these little absorption lines which turn out to come from cyanogen. And it's a doublet with a Boltzmann factor relating the depths of the two lines, and the Boltzmann factor has a temperature of 3 Kelvin or something. And this wasn't picked up on at the time, and it's partly because Hertzberg, and eventually that he wrote down in his 1950 textbook, which was literally the book on molecular spectroscopy, he commented on this and said it doesn't mean anything. And this was the CMB, right, in 1940, but it wasn't appreciated at the time. Okay, so we all know about the CMB, and why am I telling you all this stuff about photons and so on? It's because there's close analogies with neutrinos, but neutrinos are different. So this is the best plot that I've seen of the neutrino backgrounds. So this is Vitagliano et al. And what they're plotting is some units, which I don't understand because I'm only an astronomer, on the y-axis, and then energy on the x-axis. This includes neutrinos coming from the Earth, which are obviously not cosmological. It includes neutrinos coming from the sun, which are obviously not cosmological, but some parts of this are the cosmological neutrinos. And in particular, on the left-hand side here, you see the CNB. And when you first look at this, you're like, what on earth are they plotting here? Because there's these like 2 meter sticks, right, that are stuck in the middle of the thing, and that's going to be explained in a minute, right? It's not wrong. This looks wrong. I would probably multiply the y-axis by another power of energy, because then it's like doing the integral and it's proportional to energy density. So it tells you who actually matters. But they're counting neutrinos, right? Because they're particle physicists. And they just count things. Not like astronomers, where we do real physics. This is the cosmic microwave background spectrum as measured by Kobe-Firas, plus a whole bunch of other things, including the UBC rocket, which I have to say, because I'm in Canada, I come from UBC. And it's the best black body you can get, right? You can't calibrate this with a thing you can buy in the store, so you have to internally calibrate it cleverly, because you cannot make as good a black body as the CMB is. So this is the CMB and the CMB plotted together. So the thing in blue, right, is put together by these guys, and I hope you recognize, well, at least one of these guys, if you can guess who the other one is. You should recognize both of them. And the red one is the neutrino spectrum put together by these guys. And I mean, I don't have to people recognize these pictures? I mean, these are the standard pictures, right? So the blue one is the Bose-Einstein statistics, right? Because they're bosons. But the red one, they're fermions. So even if the neutrinos have a thermal spectrum, they don't have the same spectrum as the photons, right? Because there's another power of frequency on the Rayleigh-Jeans side. Do you call it the Rayleigh-Jeans side when it's for neutrinos? Yeah, still. And it's also a different temperature, right? So you'll notice that it peaks in a different place, right? So it's 1.9454 to that number of digits. Why is it smaller than the photon background? It's because neutrinos decouple before electron-positron annihilation. So the extra photons from electron-positron annihilation boost the photon background, but still thermalize, because there's processes that will just completely thermalize it. And by comparing the entropies before and after, there's a standard calculation that's in every grad cosmology course, I think. Is there a grad cosmology course there? Is that in the grad cosmology? So it's 4/11 to the 1/3, right? It's that standard thing. It's like it's an exam question. Right?
Thanks, Douglas.
Okay. You're just about to have your exam.
Correct. No, we're just about to teach the exam.
Okay. So going back to this, right? The neutrino has a different shape, but also a different peak, but you can completely predict what the neutrino spectrum should be, right? Since we're doing asides today, there's another aside. So that's Dirac on the right, right? It's this thing where you can look up your academic family tree to find out who your supervisor's supervisor is. There's one on the internet that's a very Western organized thing where everybody goes back to Jesus. Right? So you go back through sort of medieval philosophers and then to popes, and then eventually, right? And obviously that's completely biased towards the West and the Middle East eventually. And you could go back through China or India or whatever if you wanted. It's not clear once you go back a few generations what a PhD supervisor meant, right? So it gets very gray. But my supervisor was this Martin Rees guy, who some of you may know. Dennis Sciama was his supervisor. I wrote one paper with Dennis where he just told me that you can't split an infinitive and you can't start a paragraph with however. And that was about his only comment. I mean, all the ideas were his, right? And I worked on this thing, and then his final comments kind of surprised me. But never start a paragraph with however, because he's correct. Dennis had kind of three supervisors. It was a bit complicated, right? But one of them was Dirac. So Dirac is my academic great-grandfather. I missed hearing Dirac talk when I was an undergrad because nobody told me he was famous. So in first year physics, his name never comes up. He came to Edinburgh when I was an undergrad. A bunch of us said, "Who's this Dirac? What did he do?" And we didn't go. We went to the movies to see some crappy movie or something. And then in second year, his name's in every course. And we really regret it. No, and I didn't know at that time he was going to be my academic great-grandfather. So the red one is better than the blue one, is what I'm telling you. The next thing to point out is that what's plotted on the x-axis is non-trivial, right? And you have to think about it a little more. For photons, temperature redshifts, frequency redshifts, and so that guy keeps its shape, right? It's sometimes called the Tolman relation or something. And it doesn't matter whether you consider the energy or the momentum of photons, because they're the same, right? For neutrinos, it turns out it's really momentum that redshifts. And there's various ways of seeing that, but it's a fact, just accept it. So it's 1/e to the pc over kt plus 1 that keeps its shape. So you really have to think about momentum on the x-axis if you're going to make your life easy for yourself, right? And of course, E is just p squared plus m squared. So you can convert and so on, but it's much easier to think about P because it's P that redshifts. So neutrinos are complicated because you have to think about momentum states, but they also have mass. And that means that a momentum state is, with a mass, means a speed, right? So they're also all traveling at different speeds. And it's like, crap, how do I do that when I'm a CMB guy and everybody goes at the speed of light, right? There isn't a light cone. There's a neutrino cone, but there's not one neutrino cone. There's a whole spectrum of neutrino cones for all the momentum states. So much more complicated. On top of that, mass states aren't flavor states. So it's hard to answer the question, what's the mass of the electron neutrino? You can answer this, but you need matrices to do it, right? So if you learn one thing about neutrinos in the last 20 years, it's that the mass states and the flavor states are not the same. To explain that, I'm going to turn to some Canadian icons. That's Bill Shatner up in the top right, and a Canada Goose. And the Canadian icons that I'm going to turn to are Art McDonald and Timbits, right? So apologies to people who've seen this before. Lots of people will have, but there'll be young people in the room who haven't seen it before. I was told there's a new director and he says cost-saving measures that visiting speakers have to provide their own.
It's an illustrious list, including Mr. B. Pearson, Alice Monroe, and now a guy from Cape Breton. Physicist Art McDonald is Canada's latest winner of a Nobel Prize. Here to explain why he's the best in the world at what he does is Art McDonald.
Hi, I'm Art McDonald. I'm a professor emeritus at Cambridge University, based in Cape Breton. I attended Delhi University. I'm a co-winner of the 2015 Nobel Prize in Physics. People from 22 Minutes have asked me to come in and explain what our team did with this prize. We demonstrated that the flavor of the change produced in the course of electron flavors change into one of the other two flavors, muon and tau, as they travel from the core of the sun through. Neutrinos are very basic subatomic particles. We don't know how to subdivide them further. Okay, they're asking me to dumb it down a little bit. The subatomic particle is smaller than an atom. Atom is a unit of matter. You know what matter is? Okay, neutrinos are like pivots. Chocolate, cherry Phil, and sometimes they're like the old-fashioned blade. Must be the first person that ever won a Nobel Prize in 2 days.
That's good. Escape.
Okay. But that's good because that wasn't like live on the internet. So I don't know why it's taking me to. There's an AI bot noticing that I've used something from YouTube. It's connecting to YouTube. If you haven't seen that before, if you Google neutrino Timbits, it's the only. But it was super sporting of Art McDonald to do that, and it was actually, his timing was quite good for a physicist. The CNB is complicated. The thing about the CNB that's really cool is that the universe has given us this fingerprint that we can use to find out what the universe is like. So that's the anisotropies. So the CNB will also have anisotropies. Right? If you were able to detect it, there would be variations in the neutrinos from place to place. The first prediction of that was in this paper that I wrote with 3 colleagues, right? you had to work out the neutrinos to a few multiples in order to get things right. But then you can sort of cut it off and it didn't matter as long as you went to L of 4 or 5 or 6 or something. But we decided to see what happened if we went to as high an L as we could calculate, which was 1,000 and a bit, right? And what you find is that there's a rise because of the early integrated Sachs-Wolf effect. So you're changing potential going from radiation dominated to matter dominated, and that's a sort of, it's also in the cosmology class that Rene's going to teach, so ask Rene afterwards. And it turns out that that would carry on more or less as a plateau all the way until neutrino decoupling scale, right? The size of the horizon at neutrino decoupling, which is L of 10 to the 8 or something. We calculated this. My 3 collaborators all said that you know, it was sort of interesting, but we shouldn't put it in the paper because people would laugh at us. I put it in the paper, they took it out, I put it in, and then they just got tired. It stayed in the paper, right? And I said, you know, 1,000 years from now, when there's a Nobel Prize for neutrino anisotropies, we want to at least get a footnote mention. We did not include that there's a late time ISW rise because the neutrinos are changing speed, basically. So we didn't put that in deliberately. This was basically an Einstein de Sitter model. Other people have calculated the neutrino anisotropy power spectrum, and they've focused on the lowest L's, and particularly this ISW rise. This is a topic where you can read all the papers in the literature in an afternoon. So it's a sort of pretty cool thing to study because it doesn't take very long. The best predictions by far, I think, were by Elham Alipour, who was a PhD student of Chris Sigurdsson. She did publish a couple of papers. Her thesis is online, but this chapter never ended up being in a paper. That chapter is the best study of neutrino anisotropies. So you basically take a code like CAM, but then you have to wrap it in another loop for momentum. And then you have to get it right. So it takes a long time to get right, and then the code takes a long time to run because there's an extra whole loop. And she figured out how to do all of that. And these bumps and wiggles, I think, are real. It would, in principle, tell you additional information about the universe. Okay, so the summary of a bunch of that stuff is neutrinos decouple in flavor states, but they propagate in mass eigenstates, and then they would be detected in flavor eigenstates again. So if you want to make a prediction for the neutrino anisotropies, you would have to decide what your detector's like. So probably the most likely thing that you could build, if you could build anything, is an electron neutrino detector. And then it turns out, sadly, that that's, I mean, even though the mixing matrix is very off diagonal, that's mostly sensitive to the lightest neutrinos, which are the sort of least interesting in the sense that they're still relativistic, basically. But you could imagine building a neutrino detector that detects all 3 flavor states. I mean, you know, this is science fiction, so who knows? But each momentum state evolves differently, and the calculations are complicated. The anisotropies are at the 10 to the minus 5 level, and that's 10 to the minus 5 of a thing that you can't detect, right? So it's pretty hard to detect. So don't waste your time waiting for the detector to be built, because it will take a long time. But in principle, there's information all the way up to L of 10 to the 8. And the information content in the power spectrum goes like L squared. Right? And we currently go to L of 10 to the 3 or something, so there's 10 to the 5 squared times more information in principle in the neutrino anisotropies. The dipole is 100 times bigger than the other multiples. Maybe that's easy to detect. A cool thing about the dipole is that there's more than one scattering surface. So you're seeing our velocity relative to more than one thing, which may be different frames. Right? So the dipole is complicated. One of the coolest, surprisingest facts about the neutrino background is that the heaviest ones go non-relativistic early enough the decoupling surface, so the CMB last scattering surface is at redshift 10 to the 3 300,000 years ago. The neutrino last scattering surface is much earlier, but can be closer in distance than the CMB last scattering surface. And to most cosmologists, that's mind-blowing because everything's on the light column. And you can't get off the light column. It's just a fact. But here it's the neutrino column, right? So you can have something that's closer but earlier. And what that means is that in principle, and this was pointed out by Dorelson and co, but then they realized that these Russian guys had done it slightly earlier and they not missed the paper. And then Gil Holder and a student did a more up-to-date version. Train of thought is gone. Is anybody listening? What does it say?
Talking about near a bit earlier, and then
Near better. Oh yeah. So there's a really cool thing that you could do in principle. If you could measure the ISW effect or lensing in neutrinos, you could measure the depth of the potential in the neutrino background and separately the depth of the potential in the photon background at two different epochs. So there's a lot of cosmologists spend a lot of the time trying to do growth tests, and this would be a direct growth test. So that would be awesome, right? But don't hold your breath. If you could do it, it would be amazing. And then really for the neutrinos, it's not one epoch, it's all the epochs because there's all this broad scattering surface because of all the momentum states. So you could really measure the growth at a whole range of epochs. But as I say, not going to happen in the near future. The neutrino anisotropies are also complicated for another reason that's to do with them being non-relativistic. So this is a recent paper by Carlos Frank's Durham group doing n-body simulations. And what they're trying to figure out is where the neutrinos are today. So this is an inhomogeneity calculation. Right? This has nothing to do with anisotropies. So this is like what you would do for cold dark matter, but for neutrinos, they're just hotter. Right? So for cold dark matter, in principle, there's a cold dark matter last scattering surface when the particles stopped interacting. If you could see back to that, you would see anisotropies on that surface. But the cold dark matter particles get perturbed by mass. They actually get captured in halos and so on. And you don't see back to when they last interacted. For the photons, you just see the CMB last scattering surface. The perturbations are very small, it's lensing, but it's like a higher order effect. But the neutrinos are in between. So you really want a formalism that allows you to discuss anisotropies and inhomogeneities at the same time. And it's like really hard to say that fast, but that would have to be the name of the code or something. So what you really want to do is do some calculation in between, and I haven't really seen that done. So people do one thing or the other thing. The CNB would also be strongly lensed, right? In a standard lensing calculation, which might also be in Rennie's class, there's what the angle is, there's a c squared on the bottom, and there's like mass and stuff, and that c squared becomes v squared. The heaviest neutrino decouples at redshift goes non-relativistic at redshift like 100. So basically they're speed of light, and then at redshift 100, the momentum goes down like 1 plus z. I mean, really there's a curve in between, but that's basically what they do. So today they're 100 times less fast than photons, right? And that means that the gravitational bending, instead of being of order 1 arc minute like it is for the CMB, can be of order the sky. So if you look towards M31, the neutrino background is completely lensed, and a bunch of the neutrinos are captured. It's so lensed. So and that depends on the mass and the momentum and so on. It's so complicated. So maybe all we need is a better neutrino detector. But just to point out, neutrinos from the sun are hard to detect, and they're MEV, right? The cosmic neutrino background is also MeV, but it's the other M, right? So it's 10 to the 9 times different in energy, so it's really hard. I don't have my presenter display, so I have no idea what. Like for time limit, I'm not probably over already.
247.
Okay, oh, that's bad. I need more stupid side stories that are relevant. But let me end with the cosmological stuff then. So what we're doing now in cosmology is trying to constrain the neutrino parameters. So ineffective and sum of the neutrino masses are the two parameters in cosmology. Detailed calculations tell you that the effective number in neutrino flavors is slightly bigger than 3 because of a whole bunch of detailed corrections that you have to make, and there's debate over, over even maybe this digit, but certainly this digit. This is probably the best number in the literature still, so it's 3.044. So we expect there to be effectively 3.044 kinds of neutrinos, and we're trying to constrain that. The current limits are consistent with this number, but and not consistent with 2 or 4, right? But they don't tell you whether there could be a sterile neutrino. There's another sort of interesting but entirely pointless aside. This is the Planck list of cosmological parameter estimates. And if you want to write a paper on that, you're welcome to do so as well. I just need an acknowledgement, I don't know. Because it's the same number. And effective mostly changes the distance scale. Planck has an error bar of about 0.3, right? This is how it's measured. So, 2 and 4 are pretty much ruled out, but certainly 0 is very strongly ruled out, right? And that means that the neutrino background has been detected in the CMB anisotropies indirectly, but it has to be there at lots of sigma, right? Additionally, the Planck data constrain, you can put in phenomenological parameters for neutrino sound speed and anisotropic stress, which you can relate as a speed, and they both should be 1/3 for neutrinos. And these are constrained at about 2% and 10%. So we know not only that there's a relativistic background, but it has the right kind of properties to be neutrino. So the neutrino background is detected indirectly. But detecting it directly is very, very difficult. We know it's there. We know what spectrum it has. We know how the momentum behave and so on. For neutrino mass, things in cosmology depend almost entirely on the sum of the masses. There's a tiny variation depending on the individual masses, but it's not going to be detectable soon. It affects the power spectra in at least 3 different ways. So people are right now running experiments and surveys to do galaxy clustering and CMB lensing and IL CMB. And together, the hope is that you'll be able to measure the sum of neutrino masses within the next 5 years or something. Currently, the limit depends on exactly what data you use, and there are some things that peak at negative neutrino mass, which is this complication and so on. But we're a factor of 2 or 3 from what's expected from the normal hierarchy. And inverted hierarchies are already sort of dispreferred, right? They're not ruled out, but they're not preferred. And you can make plots like this, right? Where this is ruled out by neutrino oscillations, and this is maybe where we are, and we're not far off, right? So that's why there's a lot of optimism for measuring the sum of neutrino masses from cosmology. Oh, just a little thing on sterile neutrinos, because I wrote a paper with another undergrad student, Alan Nee, realizing that we measure these 2 parameters in cosmology, but if you're interested in sterile neutrinos, you measure some sterile neutrino parameters. So some mixing with a 4th neutrino mass, difference squareds, and angle in some mixing matrix that has an extra row and column. And it's really difficult to relate these because you have to be extremely careful about sampling the parameter space properly and what prior you're using. So this has often not been done properly. We wrote a paper where we did it properly, and then nobody cares. It's like only been cited by me so far. Maybe even Alan is cited. He now works on gravitational waves. So current generation cosmology experiments look set to measure the sum of neutrino masses, and that means that omega nu will be the 7th cosmological parameter, right? Or 8th if you include the CMB temperature as one of them, but normally we say it's so well measured that we don't consider it to be a parameter. So the standard model of cosmology is going to have a new parameter soon, even if there's no new crazy physics. The sum of neutrino masses can be measured. So let me finish by just saying, I first gave a version of this talk. I was at a summer school, and it was cosmology people and neutrino people. And all the talks seemed to be the same. So I thought I would make a talk that was like cosmology and neutrinos, because everybody was talking about one or the other. And this was at the Italian Physics Society's place that's on Lake Como. It's beautiful. And they have a room there called the Fermi Room, because Fermi was there and he taught in, literally taught in this room. So this is a picture of the Fermi Room. So it was sort of, it's like neutrinos, Fermi, right? If you ask the Italians whether they think, if you ask a neutrino physicist whether it's Dirac or Majorana, you get split opinions. But if you ask an Italian, it's Majorana. It's quite interesting. I mean, I'm not making that up because I asked them. But it's clearly Dirac. So this is the elephant in the Fermi room, right? I tried to make the version here, but the door was locked. So this is the elephant outside the room. So the elephant outside the room is this question, right? Will the neutrino physicists take at all seriously the measurement of the sum of neutrino masses? And I think there's some hope here, because I attended talks even 10 years ago where people from the Katrine experiment or something talked about how well they would do, and how well they would do in the future was considerably worse than the current cosmological limits, which would be fine if they even mentioned them, but because the word cosmology didn't appear in the whole talk. And you're like, are you completely unaware of this? And they said, no, but it's indirect. So I think they finally now put cosmology in their talks. They appreciate that it is indirect, but the model is really solid, right? And it doesn't mean that it's not worth doing the direct neutrino experiment. Of course it is, right? But they're complementary to each other, so they can't ignore the fact that cosmologists will measure the sum of neutrino masses. But let's see whether they really take it seriously when it happens, because it's going to happen soon. And with that, let me finish.
So it's 2:55. We've got a few minutes for questions. People need to.
Since you had so many jokes in your talk, I'll just show you what mine. But you mentioned negative neutrino mass. Do you think the last question you posed, they will believe us less if we keep posting about negative neutrino?
Don't know. I worked on the Hilly-Pop reanalysis of the Planck data with Matthew Tristan. Well, Matthew Tristan did a whole bunch of work, and I told him not to stock paragraphs with however.
Right.
And there we were surprised that our neutrino mass limits were weaker than previous reanalyses of Planck. And the reason is because it doesn't peak at negative neutrino mass. It peaks at 0. So Hilly-Pop's the best analysis of the Planck data, it peaks at 0. And if you combine that with other things, I think. So the evidence for peaking at negative is not very strong.
No, I agree.
And I don't know why people are writing papers about it.
That was the side of my question.
Could I ask a question from the over the air here, Douglas?
Yeah, I can hear you.
Okay, so I'm wondering about the history and whether you got into it of who first suggested the cosmic neutrino background. I think it must have been at some level associated with Gamow, that because basically the CMB was the CMB temperature was because of what they had done with nucleosynthesis.
Yeah.
And they said, and Gamow was the one who did the Urca process, which was a star process, but it means that he was tuned in to at least the electron neutrino part. But I'm just wondering who the first person would have been to have tried to do the cosmic neutrino background and estimate the temperature. You had it written down, you had a spectrum, you had two people on that spectrum, one of which I think was Dirac. But I don't think they were associated with the neutrino background.
Not the background, right? But no, that's a good question. I thought you were going to say it was you when you started the question.
Well, no, actually, this is quite relevant because I would like to talk about this in my in the Shad talk because
Okay.
I'm giving a huge amount of credit to Gamow for all and sundry
Yeah.
for many reasons, which I won't get into. But I'm just wondering who did this first.
It's
Because
probably the 60s or something, right? It's probably because the CMB wasn't really predicted by anybody but Gamow.
that's right. And so
So you're wondering if he
very early
also
on, I
suspected
must say,
neutrinos.
very early in the 60s, there was a Zeldovich with some other people who talked about the possibilities of neutrino masses in cosmology. That was sort of the very beginning of that. So that was the early 60s. So, they had somehow worked it out at that point. But it's an interesting issue of,
Yeah, it's a good
how they
question.
did the temperature, that the temperature was different. And of course, for a long time, until the neutral currents were discovered, they didn't have they only had the electron, well, the charge interactions, which
It's a good question. Let me try and dig and find out. I did read a lot of neutrino papers. I mean, there's not that many. So I probably came
yeah,
across
of course, and I'm kind of it's not the sort of thing that would have been burning on people's imagination
Yeah,
because it seems so remote, but it is such a remarkable concept of how, the fact is, in terms of number, the neutrinos have about the same number as the cosmic photons, but they have a lot more energy because of the mass. I mean, it's really quite startling. And, you would have expected Mother Nature would have made use of the neutrinos, not just to do this extreme hot dark matter, which is the current situation.
of course.
They might have used it to, neutrinos we know about. Why wouldn't that be associated with the dark matter? That's still a possibility with right-handed neutrinos, but
My father-in-law got super interested in history in his latter part of his life. And he was at Hertzberg. And he discovered in the Hertzberg visitor book that Gamow visited in like late 1940s or 1950 or something, when he was writing his stuff on the CMB. And McKellar was there. And apparently Gamow and McKellar both liked to go hiking. So he was trying to find out from anybody who was still alive whether there was any possibility that Gamow and McKellar spent the afternoon going up a mountain somewhere or something.
yeah, the story I heard is that I heard about this, but that Gamow, there was no connection between the McKellar discovery and the cosmic photon background, which is a
He
real
did go to the BAO, which is interesting.
yeah, it would have been one of the great stories that almost immediately after the theory there was the experimental discovery instead of having to wait 14
It's
years.
all Hertzberg's fault. My father-in-law was also a great, this is like a talk to give on stuff that I discovered about my father-in-law. But he was like an order of stuff. I mean, Ray, you probably remember Paul Feldman, right?
Yeah.
It was Hoyle that really promoted McKellar's result.
Later.
Yeah, as evidence that there was problems with the Big Bang.
But anyway, what I was going to say was we're going through my father-in-law's wardrobe, and there's a white sort of jacket thing inside a suit protector thing with a label on it. We looked at it, and it says Hertzberg's lab coat.
You just swiped it?
Probably.
But it is true that you know,
I mean, you knew Hertzberg well, so he probably literally. So we're donating it to the HAA because they need to have Hertzberg's lab coat. And if he says it's Hertzberg's lab coat, it really was Hertzberg's lab coat.
the thing that surprises me is that every single astronomer had the 3 volumes of Hertzberg on their shelf. It was the equivalent of nuclear astrophysics at the time. It was about diatomic molecules. And so it was there sitting in front of them all those years. And it wasn't until the person who I thought picked it up with cyanogen was the guy at Harvard. Name escapes me.
Purcell.
Say that again?
Purcell?
No. It was Thaddeus. Pat Thaddeus.
Oh, yeah, Thaddeus. You're right. Thaddeus did the calculation.
Yeah,
It showed it didn't couple to infrared.
well, and then as you know, cyanogen actually became one of the main ways until Kobe and Bush's experiment. It was one of the main ways to try and actually get an estimate of what the molecular background temperature was.
Before you leave.
Anyway, my own view, Douglas, is that there can still be a lot of surprises about the neutrino decoupling era. For example, you alluded to this with the spectrum because you must have put in neutrino viscous damping at neutrino decoupling. It's sort of like a silk damping, right?
I have a student who I'm trying to get to think about some things. So there ought to be spectral distortions in the neutrino spectrum, and those haven't really been calculated.
Well, that's one of the things that we're heavily on too. But the interesting question is that one could have a high degree of relative roughness in the anisotropies, in the fluctuations, that would damp away, and that could have an impact. For example, it could impact BBN, which people tried before, but they were doing extreme models, not where it's a little more perturbative. Anyway, those are really interesting questions, and my view is they're completely wide open.
Yeah, there's lots of places where you could add extra physics and see what the constraints are. For sure.
Yeah.
But detecting the standard thing is really hard. Or impossible. Probably.
Yeah, end there.
Yeah.
If anybody's interested, Douglas is talking again tomorrow at Castle Lunch.
So Douglas, presumably we know the cross section. So what sort of the physics of the detector is not going to change, and so how big a
this experiment called Ptolemy gets